Hi, it's Kate, and this is the third video of week 6 of Math 23. Now we're going to start talking about infinite series and all the kinds of language that we use to describe series and talk about their convergence and things like that. First of all, what is a series? A series is a sum of an infinite number of terms. We generally use sigma notation to talk about, finite sums that have recursive patterns within the terms, but we definitely use sigma notation to concisely write down a sum with an infinite number of terms. Let's take a look here at this notation. It's very easy to get confused between the notation we just used for sequences and the notation that we will be using here in series. So first of all, we're given an infinite series, and that's our sigma notation for the infinite series. Note that every term in the series is a sub n. So the way that would be written out is like that. A sub 1 plus a sub 2 plus a sub 3 plus ... so on and so forth. It's very important that when you use ellipses in your own arguments, that you include the very last operation before an ellipse, and if perhaps you're only talking about a finite sum, so there's a last term in there, you want to, after the ellipse, include an operation as you return, but we'll talk more about that later. But say we have an infinite series of the terms a sub n. We define the partial sum to be s sub n, that's the nth partial sum, which is equal to k equals m to n of the a sub k's. So what does that mean? Well, it looks like this written out using an ellipsis here in the middle. Note that I included the operation right before the first term that is encompassed in this ... here, and I included the operation that immediately follows the ellipse as well. That's appropriate notation, but we started the a sub nth term plus a sub m plus 1 plus a sub m plus 2 all the way up to a sub n. So this is the sum. Generally m is either 0 or 1. Most of the time I like to use 1 because then the nth partial sum is literally the sum of the first n terms. Again, really carefully looking at that notation. Before we were talking about s being a sequence. Now when we're talking about series, s is the partial sum. So really important there to think about that. We say the series, the infinite sum of the terms a sub m through up to infinity is said to converge when the limit of its partial sums as n goes to infinity equals some number s, and that number is finite. So we're looking at the sequence of the partial sums. What is the sum of the first term? What is the sum of the first two terms? What is the sum of the first three terms? And this creates a sequence. And when we're looking at this sequence of partial sums, is it approaching some number that exists and is finite? If yes, then we say the series converges, and it converges to that limit. If a series does not converge, it is said to diverge. There's no in between. A series either converges or diverges. In that case, the sum of the terms has no meaning unless its sequence of partial sums either converges to a limit that is finite, or it diverges to either positive infinity or negative infinity. You can also have something that diverges and it just does not approach the limit, just does not exist. Such a series would be 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, in which case its partial sums would be 1, 0, 1, 0, 1, 0 forever. And that's a good example of a series that diverges, but the limit of the series is not positive or negative infinity. The limit just simply does not exist. A series with all positive terms will either converge or diverge to positive infinity. Remember, we always converge to a finite value. A series with all negative terms will either converge or diverge to negative infinity. And just as the example I talked about showed, for a series with both positive and negative terms, the sum of all the terms in the series may have absolutely no meaning. It may equal nothing, right? The limit just simply does not exist. A series is called absolutely convergent if the series, which is the sum of the absolute values of each term in the series, converges. So in that case, with my example with 1 minus 1 plus 1 minus 1 plus 1, the sum of all of its absolute values would be 1 plus 1 plus 1 plus 1 plus 1 that diverges. What's interesting is that absolutely convergent series, when you remove the absolute values, when you allow the terms to change in sign, they are also convergent. When you have a series that only converges if you allow the terms to change in sign, but you don't have a convergent series when you sum the absolute values, we call that conditionally convergent, but we will be talking about that more later. Now some familiar examples of series. First, geometric series. Most of you have probably seen geometric series before. This is the form of geometric series where A here is the very first term in the series, and R is called the common ratio. And so the way you get from the first term to the next term is by multiplying by R. To get to any immediately following term, you multiply by R again, and so that's how you end up with A, then AR squared, then AR cubed. So that's why it's called the common ratio, because if you take consecutive terms and find their ratio, you'll find that it's equal to R. Now note that if the absolute value of the common ratio is less than 1, then the infinite sum here, this series, actually evaluates to A over 1 minus R. And that was one of the warm-ups that we had you guys do for class this week. It also is walked through in Ross, so something to see how exactly that works. Another type of series is a p-series, where you have 1 over n to the p. So what does that mean? Well, it might be something like this. There's an example of a p-series. Note that the denominator is changing as the index increases, and in this case, p here is equal to 2. It's the power that the denominator is raised to. And this type of series, p-series, converge if p is greater than 1, and they diverge if p is less than or equal to 1. Here's some Cauchy criterion. We say that a series satisfies the Cauchy criterion if the sequence of its partial sums, right? That's the sequence we're looking at when we think about what's the first term, what's the sum of the first 2 terms, what's the sum of the first 3 terms, what's the sum of the first 4 terms, and so on and so forth. When that sequence itself is a Cauchy sequence, so when we write that out with quantifiers, we know that for all values of epsilon, no matter how small, there's going to be some index such that any 2 partial sums beyond that index value are going to be within epsilon of each other. Here's a restatement of the Cauchy criterion, which proves more useful for some proofs, hint, hint, that no matter how small of an epsilon we take, there is going to be some index value, capital N, such that for all little n greater than or equal to little m, note that those are 2 indices that are past that capital index n. When we sum the difference between them, which note that the difference between the nth partial sum and the mth partial sum is going to be all the terms that are captured in the nth partial sum that are not in the mth partial sum. And so that's summing everything from m through to n. So that's the difference. That's just another way of rewriting this. That's like saying, what's the difference between the 5th partial sum and the 4th partial sum? Well, it's just the 5th term. That's the only term that is not counted in the 4th partial sum that is counted in the 5th partial sum. So that's like saying here are the terms that appear in the nth partial sum that are not in the mth partial sum, and the absolute value of that sum is going to be less than epsilon itself. The important result here, though, is that a series converges if and only if it satisfies the Cauchy criterion. Very, very useful.